Today we have a pretty interesting integral that I found, and I have a pretty nice solution to it. If you guys have another, maybe better solution, just leave it in the comments. But also you can pause the video and try it yourself. It is a bit challenging, so don't be too hard on yourself. And anyway, let's get into the solution. So we want to find a general formula for integral of x to the t. So we'll do something like this. And now what we can do is use Feynman's trick of differentiation under the integral sign. So we're going to differentiate both sides. And when we do that, we can actually take this d over dt inside the integral, but it becomes a partial derivative operator. And what that means is we're just going to treat x as a constant when we do that partial differentiation. So when you do that, it's going to be x to the t times the logarithm of the base, which is x, just like when you differentiate exponentials. And now we're going to let ln x equals u, but actually for the bounds to be a bit nicer, we'll just let ln x equal minus u. And that means that x is e to the minus u, and dx is minus e to the minus u du. Okay, now how do the bounds change? Well, the bottom bound becomes minus ln 0, which is just infinity, and the top bound is ln 1, which is 0. And then x was e to the minus u, so we can just replace that there and put a t, and ln x is minus u. And then dx is this monstrosity over here, so let's just put that in. And now we're just going to clean things up. So we can use, we can use this minus sign up here to change the order of the bounds, giving us infinity at the top and 0 at the bottom. And this other minus sign we'll just put at the front. And now we can combine these two exponentials, putting a 1 plus t power, and we'll just move this u to the front. Okay, now we want to let z equal t plus 1 times u, because that way the exponential's power or exponent will just be a bit nicer to deal with. So how do the bounds change? Well, they don't actually change because you have infinity times t plus 1 and 0 times t plus 1. And we're going to take t positive, which I should have mentioned. Anyway, so let's do the rest of the substitution. Du will just be dz on t plus 1. And now we can take this t plus 1, well, two of these t plus 1s outside, as t plus 1 squared in the denominator. And now we have a pretty nice integral, which you can do by integration by parts, but obviously it's just the gamma function at 2 or 1 factorial. So that's a pretty standard result. And now we're just going to integrate both sides. So we get I of t is, it's going to be 1 on t plus 1, and then plus an arbitrary constant. And we need to find this constant. So we just need an initial condition, if you will. So the integral was of x to the t, right? And when you sub in 0, you just get integrating 1, and that would just be 1. So I of 0 is 1, and that means when we plug in 0 for t, we should get 1. So that means c has to be 0 clearly, and that's pretty nice. So I of t is just 1 on 1 plus t, which is a bit difficult to work out, but luckily we did it. And now we just need to plug in I of 2, because the target integral was x squared, and that gives 1 on 1 plus 2. And I believe that's 3, but you can check that for yourself. And there we go, we are done. The integral is 1 over 3.